Hi friends, this is Dr. G. Srinivasa Gupta, professor from Department of Mechanical Engineering of VIGNANA Institute of Engineering Technology. As a part of Dynamics of Machinery course, today we are going to discuss mechanical vibrations. Last lecture we have seen briefly the water vibrations. Let us discuss more detailed way today. So as you know that vibration means a oscillatory motion of the body about its equilibrium position. When a force applied against a work on elastic constraints of the body forces, then the body is moving from its equilibrium position and gain some potential energy. At the internal forces, these elastic forces which are trying to bring back the body to its equilibrium position again. Then the potential energy which gains due to application of the force, which is going to be converted into kinetic energy. So again, because of this, the body is oscillate. Again, it gets some potential energy. In this way, transfer of kinetic energy to potential energy to kinetic energy continuously happen. The body is oscillates when there is no external resistance to stop this motion. Okay, this motion repeats periodically or non-periodically also. So for this you need to understand a model of the body object, because the elastic property the body must have. For that we are going to consider a spring element, and it has certain mass to store some energy. So the mass element we are going to consider for storing kinetic energy, and spring element for providing restoring force. Because of velocity, it will, once you release from the applied force, it is going to restore back. And one more element which is called damper, which is the external agency which tries to resist this motion. Any external cause, that we will discuss in detail coming session. For this, to explain this more clarity, we will consider a model which is called a spring element, and it has some mass. If we attach the mass to the spring, then initially spring have at this position, let us say initial position of the spring. Okay, and once you attach this mass, spring is going to get some deflection. Okay, so it is this final position, initial position is this final position. So it has got delta deflection. The mass which is attached giving the force or weight of this mass is mg. Then if you consider isolation of this mass, then obviously there will be a forces mg is downward. And what is this one? Because spring has some elastic constant k, elastic constant, or we can say stiffness coefficient k, then this is k delta is the force which is restored force. This is applied force. So based on the force balance, we can say mg equal to k delta, because it is comes under, once you attach this mass, then it has got deflection delta. It is called static deflection. This is the spring mass system. So you can see that this relation we can write k by m is g by delta. So this is actually the natural frequency of any system. We can write this is equal to natural frequency square. Okay. So natural frequency, if you want to find, then we can have k by m. This is radians per second units. Okay. So a mass attached spring move up and down. These are the examples. A vehicle suspension system, you know that spring and absorber is there, and engine components which are oscillate because of application of force. Okay. So before going to understand more clarity, with more clarity, you need to understand basic terminology that we have seen yesterday also. So what is cycle here? One complete oscillation is called cycle. Suppose this spring mass system, it is oscillating, let us say, then moving down and again moving up. This is complete cycle. Amplitude, maximum displacement it has got. Here static displacement, this is delta. Time period, period for one cycle, because it is repetition motion, oscillatory motion repetitions. For one cycle, how much time it is taken? One oscillation. That is time period. Frequency, number of cycles per second. For each unit time, how many cycles it is going to have? That is called frequency. Natural frequency, frequency at which system vibrates freely. Natural frequency means free vibration. Once you displace and leave it, no further force is applied, then it is going to oscillate continuously from its mean position. Then that is the frequency which you calculate for this, that is called natural frequency. This is the natural frequency what we are going to have written here. It is either omega n, we will use the notation, that is radians per second. We can write under square root by k by m. K is stiffness of the elastic element, that is spring here, and m is mass of that attached to that, that is that body has mass. Okay, any body, if you any object you consider, it has certain mass and some elastic property. Okay, stiffness property. These two are required to have vibrations of the body. Okay, this can also be written under square root of g by delta also. If you know delta static deflection, that you can use, and you can write natural frequency, you can find using, okay, g by delta, square root of g by delta is natural frequency. How we can write like this, we will come to know soon. So coming to types of vibrations, there is factors we have seen based on excitation, free vibration. Okay, there are no external forces are acting, just displace the body from equilibrium position and leave it. It has vibration, that is free vibration, just we talked about. Other example is pulling a spring and letting it go, that is the example we have seen just now. And forced vibrations, because of external force continuously acting, then the vibrations which causing this force is called forced vibrations. And other category is, first one is based on excitation, second one is either free or forced, second one is based on energy dissipation. Energy dissipation means external agency contribution, if it is not there, that is called undamped vibrations. Damping means absorbing energy and making it to stop. Oscillations will gradually die down. So that is damping. Okay, undamped means there is no external agency contributing to stop this oscillatory motion, that is called undamped vibrations. The motion continuously, indefinitely. So damped vibrations, there is an external agency which leads to absorption of energy, which leads to stopping the oscillatory motion. So this is so that amplitude gradually decreases, it will stop its motion. So types of damping we can provide is, we can see practical examples also later on. Light damping, critical damping, heavy damping, these are the three types of damping we can have. We can, the materials also have that such damping conditions. Now coming to other category based on linearity. Okay, first we have seen based on excitation, second we have seen based on energy dissipation, third one we have seen based on linearity. Linear vibrations, the whatever force applied or disturbance given is directly proportional to the displacement, that is linear, directly proportional. Non-linear means whatever force you apply, it is not proportional to the displacement, and the material has complex behavior of vibrations. This is based on linearity. Other category is based on motion. Longitudinal vibrations, transverse vibrations and torsional vibrations. Along the axial direction of the any suppose shaft or any component which you apply some external agency force and then leave it, oscillations are having in axial direction, then it is called longitudinal vibrations. Transverse vibration means the force of application is perpendicular to the axis, means the motion is perpendicular to the axis. Then example is beam vibration. A beam supported to supports it has, and the loads acting is transverse direction to the length, then beam is having transverse vibrations. Okay, and torsional vibrations, if you apply some twisting action, then that is angular moment. If you give angular displacement, then it is called torsional vibrations, the vibrations which occur. Then another category is based on system characteristics. It is either deterministic or undeterministic. Deterministic means predictable forces. You can have know what are the forces we have applied. Random means unpredictable forces. Okay, unpredictable forces cause the body to vibrate, and predictable forces cause the body to vibrate. This is deterministic vibrations. Unpredictable means example is earthquakes, wind loads, and all these. And machinery and all these, which are under our control, then these vibrations are predictable vibrations. Predictable forces we are applying, so deterministic vibrations these are called. We have seen simple harmonic motion, because the pendulum, if you take it, is having oscillatory motion, simple harmonic motion. Okay, so if you take same model which I have just described, spring and mass attached, then it is static deflection. Anyhow, we have written, we have seen. Then this is again displaced some after it is equilibrium position. Okay, after static deflection, then if you apply some, because that static deflection is into stiffness of the spring is same is equal to mg, that is under equilibrium. Okay, restoring force and applied, that is mass of mass self weight, which causes equilibrium both together, that is okay, it is in its main position. Now you are displaced with the x displacement along the axis of the spring. Then what happened? This is going to if you draw now free body diagram, then this is spring x displacement given, so spring stiffness is k, kx is the restoring force which is acting upward, and displacement x given. What is the equivalent force of this x? You know that force, mass spring has, and acceleration if you calculate, dx by dt is velocity, displacement is x, dx by dt velocity, and d square x by dx square. If you differentiate with respect to time twice, then you will get acceleration. So mx double dot is the acceleration. Acceleration force downwards, restoring forces, elastic restoring forces upward. So then you can write, because these two are equal in magnitude, then it is in equilibrium, then mx is minus kx, because it is magnitude wise, okay, the same, but direction is opposite. This force which is going to be applied is equal to minus of restoring force. Direction is opposite, it does mean. Other way around, you can say that one principle is called D'Alembert's principle, because acceleration of the body is downward because of given displacement, then inertia force is acts upward, magnitude is equal to, okay, acceleration forces, then these must be maintained equilibrium. That means D'Alembert's principle tells that inertia forces and whatever restoring forces of the body both together, algebraic sum of that is equal to 0. Then you can write this mx double dot plus kx like that, or this is also giving, okay, displaced force equal to restoring, so equal and opposite in direction. So you are going to get the equation plus kx equal to 0. So what is the frequency? How do you find? If you divide both all the terms with m, then you are going to get k by m x equal to 0. So then here x double dot acceleration plus this is called omega n square x, okay, equal to 0. This omega n square x is called natural frequency square term. This is k by m. So omega n is called natural frequency of any body, that is root k by m. So this is the concept of natural frequency of free vibration. This is free. Free means you have displaced and then no more force is applied, just left. Then free it is called. We are not considering any external resistance which stop this oscillatory motion. Okay. Then applications we have seen in various engineering domains. Okay, mechanical and civil and automotive and aerospace, manufacturing industry, measurements and instruments. So what is the importance of vibrations also we have seen to prevent failure due to resonance, any machinery, any system, or mechanical system or any other structural system or anything, and improve mission life and performance and safety measures also, vibration need to be analyzed, okay, and reduce noise and wear. These are the important significance of studying vibrations. Now coming to the free vibration, just we talked about free vibration. Then here restoring force I just mentioned, it is minus kx restoring force. Okay, because all the forces downward positive you take, then restoring force minus kx, then the displacement given is x, which is a function of time. So then Newton's second law tells that sum of the forces, okay, that is we are displaced with x, and that corresponding force is mx double dot, so that is equal to minus kx. So mx double dot plus kx equal to 0. The here equal sign is not uh, typed, this one mx double dot, this is equal to, okay, minus kx. So equation of motion mx double dot plus kx is 0. The standard form just mentioned, x acceleration x double dot dx square x by dx square plus omega n square x equal to 0. This is second order differential equation. So this constant, this is called natural frequency omega n square k by m. So the solution means what is the solution? X in the form we can write, because this is second order differential equation. Obviously the solution can be based on the fundamentals of differential equations, solutions of mathematics. We can write x equal to a cos omega nt plus b sin omega nt. This is a form of solution. If you substitute this and solve, you will get these constants a and b also. So this can be done straightforward. So if you consider damper also, then this mass equilibrium if you write, then restoring force due to stiffness, that is kx, and if you consider damper also, then this is cx is the c is the damping coefficient, which is a displacement stiffness per velocity. This is spring stiffness is defined as force per unit deflection. Damping coefficient is defined for force per unit velocity time. That's why Cx dot, because C into x dot, because we have given x is the displacement, then corresponding force here mx double dot, you know that acceleration force. Then these are this is the equilibrium of this mass. Okay, so then we can write mx double dot equal to minus kx minus kx minus cx dot. Okay, otherwise you can say inertia forces are acting opposite to the motion you are given, then you can say inertia force equivalent, this is minus, okay, this is opposite direction, minus mx double dot, this is also opposite direction, these are all we will use minus sign. Okay, then the sum is equal to 0, or you can write like this, this is equal to this but opposite sign. So based on the D'Alembert's principle, this one, okay, inertia force, okay, all these are same sign, or based on Newton's second law, mx double dot equal to, this is opposite direction, so minus kx minus cx dot. Both ways we can, okay, interpret this way of writing the equation. So equation of motion when damping is considered, this is mx double dot plus cx dot plus kx. Okay, here x double dot means acceleration term, x dot means velocity term, dx by dt, then x displacement. So standard form you can write this, because divide all the terms by m, then x double dot you will get c by m x dot plus k by m x. Then if you write some factor which is called zeta, damping factor, actually zeta is damping ratio it is called, that is instead of writing c by m, if you write zeta, then you should need to write in the form of x double dot plus 2 zeta omega n x dot plus omega n square x. So this zeta is called damping ratio, zeta, we can write zeta like this. This is damping ratio, which is 2 by c by 2 under square root km. Okay, this 2 root km is actually critical damping coefficient, it is called. Zeta is damping ratio, c is damping coefficient, and 2 root km we got, this is zeta damping ratio, we got c by 2 root km. This 2 root km, because c becomes equal to 2 root km value, then zeta becomes 1. Okay, this is called critical damping actually. We will discuss further this. Okay, so in this damping is also considered then free damped vibrations. It comes under it. If it is zeta is less than 1 means C is less than under 2 square root km, then it is called underdamped type of vibration. Means the resistance force external agency which is less effective on oscillatory motion, so it continues oscillations. Okay, underdamped it is. Critical damped means zeta is equal to 1, damping ratio equal to 1 means the damping coefficient becomes equal to critical damping value 2 square root km. So it will return fastest means it will oscillate but it will immediately die down. So over damped means no oscillation at all because you are applying over resistance external agency is much more effective. So that is C is greater than 2 square root km. Okay, that is this condition over damped. So immediately the oscillation part die down and no oscillations. Okay, so this is the conditions and the corresponding form of solutions in each case. Under damped case the solution, because it is also second order differential equation, okay, linear differential equation you can see here. So the solution is in the form fundamentals of mathematics of differential equations will give the solution is in the form of e power minus zeta omega nt into a cos omega dt plus b sin omega dt, where omega d is omega n square root of 1 minus j square. Actually this is omega d is damping frequency, it is called damping frequency, and in terms of natural frequency you can write 1 minus zeta square. Zeta is damping ratio. So in critical damping, that is zeta equal to 1, you have seen. Then if you substitute, because zeta equal to 1, that square root term becomes 0, omega d becomes 0. This cos omega d means 1, then sin becomes sin omega d into t. So if you write, you will get that critical damping condition, the displacement equation is a plus bt e power minus omega nt. Okay, so this is the displacement equation in critical damping. Over damping, zeta is greater than 1, then this solution will can be written as displacement is equal to ae power r1 t plus be r2t. Here r is damping, r is ratio of frequency, r is a ratio of natural ratio of frequency by natural frequency. That means for whatever damped frequency by natural frequency, that is the r here. Okay, so we will discuss more elaborately these in coming sessions also. Now other case, forced vibration with undamped, forced here, external force if you consider, then the equation can be written as mx double dot plus kx equal to the force which is going to be applied, external force continuously applying, okay, repeatedly. Then it is written as f naught sin omega t. It is in the force also, application is also sinusoidal form, then that is f naught sin omega t. Then general solution of this equation, because this is right side also, it is a differential equation not equal to 0 right side, then linear differential equation. So we know that from mathematics there is two solutions, complementary function, particular integral. Complementary function we can write as usual a cos omega nt plus b sin omega nt, and particular integral is we can write x sin omega t. So where x is maximum amplitude, this can be written as x equal to, once you substitute this xp in the equation, and you can see that you will get this complementary function, particular integral is f naught by k into 1 minus omega by omega n whole square. Okay, so final solution you write complementary function, that is a linear part of the equation solution is a cos omega nt plus b sin omega nt plus the right side quantity, other part, that will give particular integral, that is f naught by k into 1 minus omega by omega n means r, as I mentioned. We are using notation 1 minus r square, okay, into, okay, sin omega t. This is the form of solution. Okay, so again another case, previous case we have seen forced vibration with undamped. If you add damping coefficient, damping part, then equation subsequently written as mx double dot plus cx dot plus kx equal to f naught sin omega t. So here also solution is linear portion of the that equation left side, that solution is we can write as usual, and this right side part also we can write solution. So if you know maximum amplitude, then you can straightforward write x displacement is x times maximum amplitude times sin omega t minus pi. Because damping is contributing, that term will come in the form of omega t minus phi. Phi is the phase angle. That phase angle also we can find. Okay, amplitude is x maximum amplitude, that is f naught by k whole by square root of 1 minus r square whole square plus 2 zeta r whole square under square root, these are terms. So this is the amplitude we can find, okay, where r is omega by omega. And phase angle phi here is tan inverse 2 zeta r by 1 minus r square. This is the phase angle. So as for from the fundamentals of mathematics, these are all are second order differential equations, and if there is a right side equal to some force component, then we are having this particular integral also, okay, complementary solution and particular integral term also we can add if that is forced vibration with damping, without damping also the term will come accordingly. Okay, this is about this type of four types of vibrations. Free vibrations, undamped it is called, no damping phenomena. Second one is free vibration with damping. Third one is forced vibrations without damping. Fourth one is forced vibrations with damping. Corresponding equations. Okay, damping ratio will come, say if it is there in the damping. Wherever is damping is there, then it is, we will have some damping ratio term. Okay, that is zeta, right? Okay, this is about all these types of vibrations, corresponding expressions we can develop, and we can use these for, okay, analyzing further. Okay, so here one example I have taken, D'Alembert's principle. Using D'Alembert's principle, how can we write equation? So you know that D'Alembert's principle tells that applied forces and inertia forces algebraic sum must be zero. Then what is inertia force? Inertia force, just I mentioned, explained, that is minus mx double dot, that is force, inertia force, opposite to the motion, direction of displacement. Then you have seen that restoring forces acting, okay, upward direction. So all downward forces considered are positive. Then you can write this sum of the forces in this form, minus kx minus cx double dot minus mx double dot is 0. So rearranging, we can get same result as Newton's method. So another method, energy method also. Total energy must be balanced. Then you can write total energy and differentiation of total energy with respect to the displacement must be 0. Then it is in okay, equilibrium position. Then kinetic energy we can write half mx mv square, we will write half m x dot square. And potential energy is because stiffness coefficient k, potential energy we can write half k x square. Then sum of these energies, kinetic energy and potential energy, if you differentiate with respect to time, must be 0. That is called law of energy conservation. So then there is no energy loss, energy gain, and total energy transformation. Total energy is constant. So differentiation with respect to time, energy is not gained and lost. Then d by dt of t plus v, total kinetic and potential energy terms must be 0. Okay, t you have written and differentiate. Then you have mx double of mv square you have written. Then okay, v square term, if you differentiate, you will get mx dot x double dot plus kx x dot equal to 0. So dividing by x dot will give same equation. Okay, this way you can have different approaches. Energy conservation approach, that means total energy method it is called, or you can have apply D'Amber's principle, or you can apply Newton's second law. So Newton's method. So these are all various approaches. We can develop these equations using any of these approaches. Further analysis of these equations we will see in our coming lectures. Overall I can say, so these are 4 vibrations: undamped free, damped free, forced undamped, and forced damped. So these corresponding equations we can see how we can write these equations, and based on either approach, Newton's law, or energy approach, or energy approach, or Newton's law, or D'Alembert's principle. Okay, any of these. Okay, with this I am ending this lecture here. We can meet in our next lecture.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.